Today we embark on a journey into the strange and fascinating world of antimatter. It sounds like something straight out of science fiction, doesn't it? But I assure you, it's very real. And it might hold the key to unlocking some of the universe's greatest mysteries. Antimatter is the bizarre twin of ordinary matter. For every particle of matter there exists an antiparticle with the same mass, but opposite charge. Imagine a mirror universe where everything is flipped. That's essentially what we're talking about. But this isn't just a theoretical concept. Antimatter has been observed in laboratories, albeit in minuscule quantities. And its existence raises profound questions about the fundamental nature of our universe. Why is there more matter than antimatter? What happened to all the antimatter after the Big Bang? These are just a few of the questions that keep physicists up at night. Imagine a world where charges are reversed. Electrons, normally negatively charged, would be positively charged positrons. Protons, the positively charged heart of an atom, would become negatively charged antiprotons. It's mind-boggling. But here's the kicker. When matter and antimatter meet, they annihilate each other in a burst of pure energy. It's the ultimate example of E equals mc squared, Einstein's famous equation that demonstrates the incredible energy stored within matter itself. This explosive reaction has captured the imaginations of scientists and science fiction writers alike. Could antimatter be the ultimate fuel source? Could it power starships to distant galaxies? The possibilities, while still theoretical, are noteworthy. However, harnessing the power of antimatter is no walk in the park. Producing and containing it is a monumental challenge, one that pushes the very limits of our technological prowess. Despite the challenges, the pursuit of understanding antimatter is more than just a scientific curiosity. It has the potential to revolutionize our understanding of the universe and our place within it. By studying antimatter, we're essentially peering back in time, trying to unravel the events that transpired during the Big Bang. We're looking for clues to explain why the universe is the way it is, why we exist at all. So, join me as we delve deeper into the mysteries of antimatter. We'll explore its potential applications, from medicine to energy production, and examine its role in shaping the cosmos as we know it. Get ready for a mind-bending journey. As we've established, antimatter is not something you stumble upon in your backyard. It's incredibly rare in the universe as we know it, and producing it here on Earth is a monumental task, even for the brightest minds in physics. You see, creating antimatter requires immense amounts of energy. We're talking about smashing particles together at nearly the speed of light in massive particle accelerators like the Large Hadron Collider. These machines are marvels of engineering, but even they produce antimatter only in minuscule amounts. To give you an idea of the scale, it would take billions of years to produce even a gram of antimatter using our current technology. That's why antimatter is often dubbed the most expensive substance on Earth. It's estimated that a single gram could cost upwards of $60 trillion. But the challenges don't stop there. Once we manage to create antimatter, we face the daunting task of containing it. Remember what happens when matter and antimatter meet? It's not pretty. Containing antimatter is like trying to hold lightning in a bottle. It's highly reactive and wants to annihilate with any matter it touches. So, we have to get creative. Scientists have devised ingenious traps that use magnetic and electric fields to suspend antimatter particles, preventing them from coming into contact with ordinary matter. These traps are incredibly complex and require precise control. Imagine trying to levitate a feather using only magnets. Now imagine that the feather explodes on contact with anything else. That's the level of precision we're talking about. But even with these sophisticated traps, we can only contain antimatter for limited periods. The longest we've managed is around 16 minutes for a cloud of antihydrogen atoms. It's a remarkable feat, but it highlights the challenges we face in studying and utilizing antimatter. The difficulty in producing and containing antimatter translates into a hefty price tag. As I mentioned earlier, a single gram is estimated to cost trillions of dollars. To put that into perspective, that's more than the entire GDP of most countries. So, while the potential applications of antimatter are vast, its cost remains a significant barrier to widespread research and development. However, don't lose hope just yet. Scientists are constantly working on new techniques to produce and trap antimatter more efficiently. As technology advances, we can expect the cost to decrease, opening up exciting possibilities in the future. But the high cost of antimatter also raises intriguing questions about the early universe. Now, let's take a step back and consider a fundamental mystery related to antimatter. According to our current understanding of physics, Matter and antimatter should have been created in equal amounts during the Big Bang. But here's the catch. If that were the case, the universe wouldn't exist as we know it. All the matter and antimatter would have annihilated each other, leaving behind a sea of energy. So why do we live in a universe dominated by matter? Why is there this apparent asymmetry? This question has puzzled physicists for decades and remains one of the biggest unsolved mysteries in cosmology. One theory suggests that there might be a slight imbalance in the laws of physics that favor matter over antimatter. This tiny imbalance, even 1 part in a billion, could explain why we see so much matter and so little antimatter today. The mystery of the matter-antimatter asymmetry takes us back to the very beginning of the universe, the Big Bang. By studying antimatter, we're essentially trying to piece together the events that unfolded during those first fleeting moments of existence. Some scientists believe that by studying the properties of antimatter, we might uncover subtle differences in the way it behaves compared to matter. These differences, however small, could hold the key to understanding why matter prevailed in the early universe. Others are searching for primordial antimatter, remnants from the Big Bang that might still be lurking in the far reaches of the cosmos. Detecting even a tiny amount of primordial antimatter would be a monumental discovery, providing invaluable insights into the early universe. Despite the challenges and mysteries surrounding antimatter, its potential applications are vast and captivating. Imagine a future where antimatter powers spaceships to distant stars, its immense energy density allowing us to explore the galaxy at unprecedented speeds. Or picture medical treatments using antimatter beams to target and destroy cancer cells with incredible precision, minimizing damage to healthy tissue. These applications might seem like science fiction today, but so did many of our current technologies just a few decades ago. As our understanding of antimatter grows, so too will our ability to harness its power for the betterment of humanity. The journey into the world of antimatter is just beginning. As we continue to explore its properties and unravel its secrets, we're likely to uncover even more profound insights into the nature of the universe and our place within it. Antimatter releases energy with unparalleled efficiency. When matter and antimatter collide, they annihilate, converting their mass into pure energy. This isn't a typical reaction, like burning wood or a nuclear bomb. It's a complete conversion, governed by E=mc². A gram of antimatter could produce an explosion equivalent to Hiroshima. It's a mind-boggling amount of power in a tiny substance. This energy density makes antimatter a prospect for revolutionary applications. The sheer energy density of antimatter has sparked countless dreams of a future where this exotic substance fuels our civilization. Imagine a world free from fossil fuels, where power plants generate clean, safe energy through matter-antimatter annihilation. However, several hurdles stand between us and this utopian vision. Firstly, as we've established, producing even a minuscule amount of antimatter is incredibly expensive and energy-intensive. Secondly, storing and transporting antimatter safely pose immense logistical challenges. Remember, any accidental contact with ordinary matter would result in a catastrophic release of energy. Despite these hurdles, the potential benefits of antimatter energy are too significant to ignore. Researchers are actively exploring new methods for producing, trapping, and manipulating antimatter, hoping to one day unlock its full potential as a revolutionary energy source. While a world entirely powered by antimatter may remain a distant dream for now, its potential applications extend far beyond just keeping the lights on. Beyond the realm of energy production, antimatter holds immense promise in the field of medicine, particularly in the fight against cancer. One promising application is anti-proton therapy, a highly targeted form of radiation therapy. In conventional radiation therapy, high-energy beams are directed at tumors, but these beams also damage healthy tissue along their path. Anti-proton therapy offers a more targeted approach. Antiprotons, when directed at a tumor, release their energy with incredible precision, minimizing damage to surrounding healthy cells. Clinical trials have shown promising results for anti-proton therapy, particularly in treating deep-seated tumors that are difficult to reach with traditional methods. While still in its early stages, anti-proton therapy represents a potential game-changer in cancer treatment, offering hope for a more effective and less invasive approach. Beyond cancer treatment, the unique properties of antimatter could revolutionize medical imaging and diagnostics, paving the way for earlier and more accurate disease detection. For decades, science fiction writers have envisioned spacecraft hurtling through the cosmos at incredible speeds, powered by antimatter engines. While this remains firmly in the realm of speculation, The physics of antimatter propulsion is surprisingly sound. Remember the incredible energy density of matter-antimatter annihilation? That energy, if harnessed effectively, could propel a spacecraft to a significant fraction of the speed of light, making interstellar travel a tangible possibility. Of course, numerous engineering challenges must be overcome before we can even contemplate building an antimatter engine. We would need to produce and store vast amounts of antimatter, design a system to control and direct the annihilation reaction, and develop shielding to protect the spacecraft from the intense radiation generated. Despite these challenges, the allure of interstellar travel fueled by antimatter continues to captivate scientists and dreamers alike. While it may be generations before we witness the launch of the first antimatter-powered spacecraft, the possibility, however distant, remains an enticing goal. Beyond its potential applications, antimatter serves as a powerful tool for probing the fundamental mysteries of the universe. By studying the properties of antimatter and its interactions with matter, physicists hope to unravel some of the most perplexing questions about the cosmos. One such mystery is the existence of dark matter, an invisible substance believed to make up a significant portion of the universe's mass. Some theories propose that dark matter might interact with itself through a process that produces antimatter, offering a potential avenue for detection. Furthermore, the study of antimatter could shed light on the matter-antimatter asymmetry problem, which we touched upon earlier. Why is our universe dominated by matter, when equal amounts of matter and antimatter should have been created during the Big Bang? By carefully examining the properties of antimatter, physicists hope to find subtle differences that could explain this puzzling imbalance. In a sense, antimatter acts as a cosmic detective, offering clues to the universe's hidden secrets and helping us piece together the story of its origin and evolution. As we've explored, antimatter holds immense promise as a revolutionary source of energy, a powerful tool for medical advancement, and a key to unlocking the mysteries of the universe. However, significant challenges remain in harnessing its power and realizing its full potential. The high cost of production, the difficulties in containment, and the need for technological breakthroughs all pose formidable obstacles. Yet, the potential rewards of antimatter research are too great to ignore. Continued investment in research and development is crucial for overcoming these challenges and unlocking the transformative power of antimatter. While a future entirely fueled by antimatter may remain a distant dream for now, its potential to revolutionize energy production, medicine, and space exploration is undeniable. As we continue to explore the strange and fascinating world of antimatter, we inch closer to realizing its extraordinary potential and shaping a future that may seem like science fiction today. In the heart of CERN lies the Anti-Hydrogen Laser Physics Apparatus, or ALPHA experiment. Scientists have achieved a groundbreaking feat trapping and studying antihydrogen. Imagine trying to hold a wisp of smoke. That's the challenge of trapping antimatter. Antihydrogen annihilates upon contact with ordinary matter. The ALPHA team uses magnetic fields to suspend antihydrogen atoms in a vacuum. This allows precise study of antihydrogen's properties. One of the fundamental questions surrounding antimatter is its gravitational interaction. Does antimatter fall down, like ordinary matter, or does it fall up? This seemingly simple question has profound implications for our understanding of gravity and the nature of the universe. According to Einstein's theory of general relativity, gravity is not a force but a curvature of space-time caused by the presence of mass and energy. If antimatter has negative gravitational mass, it would imply a repulsive gravitational interaction between matter and antimatter, a concept that challenges our fundamental understanding of gravity. While measuring the gravitational interaction of antimatter is incredibly challenging, experiments like ALPHA are making progress. By carefully tracking the motion of trapped antihydrogen atoms, scientists hope to determine whether they fall up or down in Earth's gravitational field. Answering this fundamental question could revolutionize our understanding of gravity, potentially leading to new physics beyond the standard model, and offering insights into the behavior of the universe at its earliest moments. High above Earth, hurtling through space at nearly the speed of light, lies another tool in our quest to understand antimatter, the Alpha Magnetic Spectrometer, or AMS. This remarkable instrument, mounted on the International Space Station, acts as a cosmic ray observatory, searching for telltale signs of antimatter particles among the constant barrage of cosmic radiation. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that originate from distant sources in our galaxy and beyond. These particles, accelerated to incredible speeds by supernova explosions and other astrophysical phenomena, provide a unique window into the universe's most energetic processes. The AMS experiment, with its powerful magnets and sensitive detectors, can identify and measure the properties of these cosmic particles with remarkable precision. Among the billions of particles detected, scientists are searching for a rare few antimatter particles such as antiprotons and antihelium nuclei. Finding these antimatter particles in cosmic rays would have profound implications, potentially hinting at the existence of large-scale antimatter structures in the universe such as antistars or even entire anti-galaxies. In 2016, the AMS collaboration announced an intriguing discovery: a handful of antihelium nuclei detected among the billions of cosmic rays analyzed. This finding, while statistically limited, sent ripples through the scientific community, raising more questions than answers. Antihelium, consisting of 2 antiprotons and 2 antineutrons, is incredibly rare in the universe as we know it. While antiprotons can be produced in high-energy collisions, such as those occurring in cosmic ray interactions, creating an antihelium nucleus requires a much rarer and more energetic process. The detection of even a few antihelium nuclei suggests the possibility of antimatter sources within our galaxy, such as antistars or remnants of primordial antimatter from the Big Bang. Another intriguing possibility is the existence of mirror matter, a hypothetical form of matter that interacts with our universe primarily through gravity, potentially harboring significant amounts of antimatter. While the origin of the observed antihelium remains a mystery, its detection highlights the potential for groundbreaking discoveries in the realm of antimatter research and underscores the universe's capacity for surprises. The detection of antihelium in cosmic rays has fueled speculation about the existence of large-scale antimatter structures in the universe, such as antistars, anti-galaxies, or even entire antimatter domains. While our observable universe appears to be dominated by matter, the possibility of antimatter hiding in distant regions remains an intriguing possibility. Detecting such structures, however, is a monumental challenge. Antimatter galaxies, if they exist, would emit light that is indistinguishable from ordinary matter. The only way to differentiate them would be through their interactions with the surrounding intergalactic medium, potentially producing faint annihilation signatures. Several telescopes, both ground-based and space-based, are actively searching for these telltale signs of antimatter annihilation, scanning the distant universe for faint excesses of gamma rays, the most energetic form of light, which could signal the presence of antimatter. While no conclusive evidence for antimatter galaxies has been found yet, the search continues, driven by the tantalizing possibility of uncovering a hidden side to our universe, a mirror image where antimatter reigns supreme. Antimatter plays a crucial role in testing the fundamental symmetries of our universe. CPT symmetry states that the laws of physics are unchanged under charge conjugation, parity transformation, and time reversal. Experiments with antimatter, such as those at CERN, provide stringent tests of CPT symmetry. Comparing antimatter and matter properties helps probe for any violations of this fundamental symmetry. The study of antimatter has come a long way since its theoretical prediction nearly a century ago. From the first glimpses of antimatter particles in cosmic rays, to the creation and trapping of antiatoms in laboratories, each discovery has deepened our understanding of this enigmatic substance. As technology advances, we can expect even more groundbreaking discoveries. New generations of particle accelerators will allow us to create and study antimatter in larger quantities, probing its properties and interactions with unprecedented detail. Space-based observatories will continue to scan the cosmos for hints of antimatter, searching for antistars, anti-galaxies, and other exotic phenomena. The quest to understand antimatter is a journey into the heart of the unknown, a pursuit driven by our insatiable curiosity and our desire to unravel the universe's deepest secrets. Let's rewind the cosmic clock, way back to the very beginning, to the inferno of the Big Bang. In those first fleeting fractions of a second, the universe was a maelstrom of energy, a seething cauldron where particles and antiparticles were constantly popping in and out of existence. According to our current understanding of particle physics, matter and antimatter should have been created in equal amounts during the Big Bang. It's like a cosmic balancing act. For every particle of matter, there should have been a corresponding antiparticle, its mirror twin with the opposite charge. This symmetry, however, creates a profound paradox. If matter and antimatter were truly created in equal measure, they should have annihilated each other completely, leaving behind nothing but a sea of radiation. No galaxies, no stars, no planets, and certainly no us. So, the question that keeps cosmologists awake at night is this. Why do we live in a universe dominated by matter? Where did all the antimatter go? This is the crux of the matter-antimatter asymmetry problem, one of the most profound mysteries in modern cosmology. To understand the missing antimatter, we journey back to the annihilation era, a brief but dramatic period in the universe's infancy. A seething soup of particles and antiparticles constantly colliding and annihilating each other. They vanish in a puff of energy, only to be replaced by another pair popping into existence. This released unimaginable energy, fueling the universe's rapid expansion. A crucial imbalance emerged, a slight excess of matter over antimatter. This tiny surplus forms the basis for all the stars, galaxies, planets, and life we observe today. The question of why matter won out over antimatter in the early universe is like a cosmic whodunit. We have the crime scene, the present-day universe with its abundance of matter and dearth of antimatter. But the culprit, the mechanism responsible for this cosmic imbalance, remains elusive. Physicists have proposed various theories to explain this asymmetry, invoking new particles, new forces, or subtle flaws in the fundamental symmetries of nature. One leading contender is the idea of CP violation, a phenomenon that suggests a slight difference in the behavior of matter and antimatter under certain circumstances. Imagine a mirror that doesn't quite reflect things perfectly. CP violation is like that. It implies that the laws of physics might not be entirely symmetrical when it comes to matter and antimatter. This tiny imperfection, if it exists, could have tipped the scales in favor of matter during the early universe. However, the amount of CP violation observed in particle physics experiments so far seems insufficient to explain the observed matter-antimatter asymmetry, leaving the door open for new physics and alternative explanations. The search for the source of the matter-antimatter asymmetry is a multifaceted endeavor, involving experiments at giant particle accelerators, observations of distant cosmic phenomena, and theoretical work pushing the boundaries of our understanding of fundamental physics. At CERN, experiments like LHCb are studying the decays of particles containing bottom quarks, searching for tiny differences in the behavior of matter and antimatter that could provide clues to CP violation. Other experiments are looking for rare processes such as the decay of a muon into an electron and a photon, which are predicted to occur at different rates for matter and antimatter. Meanwhile, astrophysical observations are scanning the distant universe for signs of primordial antimatter, remnants from the Big Bang that could provide insights into the conditions of the early universe and potentially reveal hints of the asymmetry's origin. The quest to understand the matter-antimatter asymmetry is a profound scientific challenge, but it's this pursuit of knowledge, this relentless questioning of the universe's inner workings, that drives our understanding of the cosmos forward. Detecting antimatter from the Big Bang would revolutionize our understanding of fundamental physics. One approach is to look for its annihilation signature in the cosmic microwave background, or CMB. Matter and antimatter annihilate, producing high-energy gamma rays. Observations of the CMB have yet to reveal conclusive evidence for primordial antimatter. As if the mystery of the missing antimatter weren't enough, there's another cosmic enigma that might be intertwined with it. Dark matter. This elusive substance, invisible to our telescopes, makes up a significant portion of the universe's mass, its gravitational influence holding galaxies together and shaping the cosmic web we observe. While we don't know what dark matter is made of, some theories propose that it could interact with itself through a new type of force, and this interaction might produce a small amount of antimatter as a byproduct. If this scenario is correct, then detecting this antimatter could provide indirect evidence for dark matter and shed light on its elusive nature. Several experiments are searching for signs of dark matter annihilation, looking for excesses of antimatter particles such as positrons and antiprotons in cosmic rays. The connection between dark matter and antimatter is still speculative, but it highlights the interconnectedness of the universe's mysteries, how seemingly unrelated phenomena might be linked in ways we are only beginning to understand. As we've journeyed through the cosmos of antimatter, we've encountered mind-boggling concepts and tantalizing possibilities. Imagine a substance so powerful that a single gram could rival the energy of an atomic bomb. That's the incredible potential of antimatter, the mirror twin of ordinary matter. Why is there more matter than antimatter when the Big Bang should have created them in equal amounts? This cosmic imbalance remains one of the most perplexing mysteries in modern physics. Experiments like ALPHA at CERN are meticulously studying antihydrogen, hoping to unlock its secrets and glimpse new physics. The AMS experiment scours the cosmos for signs of antimatter and cosmic rays. Detecting even a single anti-helium nucleus sends ripples through the scientific community. The study of antimatter could revolutionize our understanding of the universe, shedding light on the Big Bang and dark matter. By piecing together clues from experiments and observations, we're unraveling the story of antimatter. Imagine a universe where antimatter dominates, with stars and galaxies made of anti-atoms. The connection between antimatter and dark matter is mind-blowing. Detecting antimatter could provide evidence for dark matter. The quest to understand antimatter drives scientific exploration, pushing the boundaries of human knowledge. As we look ahead to the future of antimatter research, the possibilities are vast and awe-inspiring. New generations of particle accelerators will allow us to create and study antimatter in greater quantities. Imagine a future where antimatter is a powerful tool for energy production, medical treatments, and interstellar travel. The journey to understand antimatter is a testament to the human spirit of exploration and curiosity. Thank you for joining me on this incredible journey into the world of antimatter. I hope this exploration has sparked your curiosity and left you with a sense of wonder about the universe and the mysteries it holds. If there are any burning questions about antimatter or any other cosmic topic you'd like to explore, please share your thoughts in the comments section below. I'd love to hear from you. And as always, thank you for watching Time Pilgrimage. Don't forget to subscribe and like if you enjoyed this video. Until next time, keep exploring the cosmos.